Hi, I'm Craig Putnam, a robotics engineering professor here at WPI, and this is the first of a series of videos on operational amplifiers, or op-amps. Op-amps are extremely versatile devices. We use them in lots and lots of different kinds of applications. They can be used to handle things like multiplication, division, addition, subtraction, all sorts of things. We're going to start simply and then move into more detail as we go on through these videos. We're going to start by building a model of our ideal op-amp. By model, I mean a collection of equations that governs the behavior of the op-amp. So we'll be able to use these equations to say, here's how it's going to act in different situations. We're going to start with a simple model, and then we'll build up and get to more detail later on in some subsequent videos. Now, the first thing to understand about op-amps is that they are an active device. So unlike resistors and capacitors, which you might have worked with before, those are passive devices. There's no power supply or anything that's necessary in order for them to be able to do what they do. An op-amp, on the other hand, you do need a power supply. There's going to be connections to the power supply, and we'll include those in our model later on, but for the time being, we're not going to show those. We'll get to that level of detail later. So for the moment, we're just going to concentrate on the input and output terminals for our op-amp. Op-amps typically have just 3 terminals. 2 of these are input terminals, and 1 is an output. The 2 input terminals are labeled inverting and non-inverting, and are assigned a minus and a plus sign respectively. An op-amp amplifies the difference in voltages between these terminals by a constant gain value labeled A here. Ideally, when the op-amp is configured as shown in what is known as an open loop configuration, the gain value is very, very large, and we treat it as infinite in our idealized model. As a side note, there's another configuration called closed loop. We'll discuss that one later. So how does the output of the op-amp relate to the inputs? That relationship is given by this equation. As you can see, the output voltage is the difference between the non-inverting voltage, labeled V plus here, and the inverting voltage, labeled V minus, times that gain constant A. So if the difference between the input voltages is 0, then the output voltage will also be 0. This equation governs the essential behavior of our op-amp. What we've developed here is an idealized model. We'll refine it as we go along. We're going to get to the point of where we can make some better estimations of the behavior of the op-amp from these refined models. We're also going to look at how we can put op-amps to practical use. So just as a reminder, we need to come back now to discuss how the op-amp is powered, okay, because it's an active device. All right? Let's look at these 2 additional connections that we're going to have. They're labeled V++ and V-. They're also called the rail voltages sometimes. This is where we begin to refine our model. The rail voltages are going to come into play in that refinement. Now, the equation that we have for our ideal model says that the output voltage is going to be the gain constant times the difference of the 2 input voltages. If you have even a tiny difference in those input voltages, the output voltage can get to be very, very large because the gain constant is very, very large. So here's the key thing. If our rail voltages are now brought into the model, they're going to limit the output voltage. You can't have an output voltage that's bigger than either of the rail voltages. And so this is our first refinement of our idealized model, is bringing these rail voltages into play. So if the difference between V plus and V minus is slightly positive, then the output is going to try to be huge, a huge positive value. And in fact, you can only send the output positive to the rail voltage V++. Similarly, if the difference between the input voltages is slightly negative, then it's going to try and drive the output to a large negative number, but it gets limited by the V minus rail voltage. So when the output voltage hits one of those limits, either the V++ limit or the V minus limit, we're saying that the op-amp becomes saturated. and that's the term that's commonly used to describe that. I do at this point need to add a little bit of refinement to our model. Most real op amps won't let the output voltage go all the way to the rail voltage. So for example, if our rail voltages were positive 5 volts and 0 volts, the output voltage might be limited to, for example, 4.7 volts and 0.3 of a volt. There are op amps that will let you go all the way to the rail voltages, but they're a subset of all op amps. Those are called rail-to-rail op amps. They exist, but you don't see them quite so commonly. The way you can tell how close you can get to the rail voltage is by looking at the spec sheet for your particular op amp. The details will be in the spec sheet. Okay, so now let's see how we can exploit the behavior of this open loop op amp configuration. Suppose we have a robot with a sensor that reacts to the intensity of light falling on it. And further, suppose we want to know whether the light intensity is above or below some particular level. In this example, we'll use a photoresistor or light-sensitive resistor and an operational amplifier operating as a comparator. Let's set up this LM741 op-amp circuit on a prototyping board. We'll connect the photoresistor or sensing circuit to the non-inverting input terminal. This sensing circuit is made up of a voltage source of 5 volts going through a voltage divider, where one of the resistors in the divider is the actual photoresistor. Basically, the voltage divider outputs some fraction of the source voltage here, depending on how much light is falling on the photoresistor. Next, we'll set up a potentiometer, also having a source of 5 volts, on the inverting op-amp input. A potentiometer is a device with a resistive strip on the inside that can also be treated as a voltage divider. We can use it in this case to set a reference voltage at the inverting input of the op-amp. Now let's connect an LED with a series resistor to the op-amp's output. This will let us know whether or not the light intensity is above or below some threshold value that we can set using the potentiometer. We've also given our operational amplifier supply voltages of plus 5 volts and ground. This way, if the inverting input is larger than the reference voltage, the output voltage will be 0 and the LED will not be illuminated. Conversely, if the non-inverting voltage is larger, the op-amp will output 5 volts, lighting up our LED. We know that the photoresistor has a larger resistance in low light, so we can expect the voltage at the non-inverting input will be at a higher potential than the reference voltage we set using our potentiometer. We set the potentiometer such that when the photoresistor is in bright light, in other words above the threshold, the non-inverting terminal is at a higher voltage than the reference. This causes the op-amp to amplify the now positive difference between the input voltages. Because the op-amp's output voltage range is limited by the power supply, the device outputs V++, the positive rail voltage of 5 volts, illuminating the LED. In this way, an op-amp without feedback can be made to operate as a comparator. Now, a comparator is simply a component, an op-amp, that compares two input voltages and outputs an output voltage which is going to be a binary or two-state representation of what's going on with the input voltages. As you can see in this case, if the input voltage is slightly higher, slightly more positive than the reference voltage, then the output voltage is going to be positive and it's going to go all the way up to the V++ rail voltage. On the other hand, if the input voltage is slightly less than the reference voltage, then the output is going to get driven into the other rail, the V-minus rail. And those are the only two states that we really can get for output voltages, all the way at one rail or all the way at the other rail. As was mentioned earlier, this is an example of where we use the open loop configuration of our op-amp. In the next video, we'll look at closed loop op-amp circuits and how they may be used.